Hey, recently I had what I think is a really cool breakthrough, and I wanted to share it with you. And so I figured I would just jump into kind of where I am in the middle of my work. And if this is the sort of thing that interests you, then you're certainly invited to follow along. What I'm going to show you here is this little micro tool that we made in order to eventually create Option, the app. So this is the old version of Option. Over here, I'm all zoomed in now because you have to zoom in because the text was made really small because it was made by an idiot. Um, uh, but it's now getting a refresh, and you can see that the core of this game is that you make a statement and then you make an invalidating statement underneath it. And those invalidating statements themselves can have invalidating statements and so on. And so this is called a point, and this is called an invalidating point. And the vision here is that you can have a Twitter-like surface, kind of like Warpcast, where people can cast in response to these statements, and these are negating statements to one another, and then that those negations eventually together help to create a kind of collective intelligence. And you might think, well, that sounds really nice, but is it really appropriate to call it collective intelligence? And that's what I want to show you. So that's the breakthrough of the day, actually of Sunday, is exactly how that collective intelligence emerges out of this graph. And I'll show you how that works in detail right after this. But first, I want to show you how in Warpcast, really in any platform that allows quote tweeting, you can encode this kind of structure. So here we have our top level point. The Earth is flat. Here we have a bunch of invalidating points underneath it. And these invalidating points are quote casted for reasons that we might or might not get into in this conversation. But essentially what it says is that it's relevant here. So this outer cast is saying this is relevant, and the inner cast is saying what's the thing, the object level claim that you're saying is true. And that's important because if you don't have a notion of relevance in your system, then the higher order collective intelligence part isn't able to work because for reasons that you'll see, you'll be able to abuse it. And so here we are looking at the underlying code, which actually enables us to give a final score. That final score is called a credence, a final score to a graph. And I'm going to show you what that means in just a second here. So to begin with, let's start just by introducing you to the tool. So these are called deltas that we're going to build up. And then these deltas can be things like a point. Let's say that the point is the Earth is flat. And then you can have an invalidating point, which says the Earth is round. And then you can link the two. So you can say, well, let me actually first graph this for you. So graph and then build, I think, deltas. And we get our two little points here. Here's 0.0 and here's 0.1. This all could be a lot prettier because, you could imagine it actually says something on here, but this is just me working on the math part of it. So it doesn't need to be a perfect user interface. Okay, so now what I want to show you is that we can link these two. So we can say that what a link does is it's saying that if the source is true, then that is evidence that the target is not true. So if it's true that the Earth is flat, then that negates the idea that the target, that the Earth is round, is true, right? And then vice versa. If you had evidence that the Earth is round, that would be evidence against the idea of the Earth being flat. And so now when we build this, we get this diamond shape, right? Because 0 is negating 1, and 1 is negating 0 through these little points. And maybe as a brief diversion, let me show you why we need these relevant points, why we need these quote casts, which have their own score of relevance in addition to having their own score of veracity. The reason we need this is because I could write a point here that says the speed of light is greater than 15 kilometers per hour. And then I could say link that to the Earth is flat. I didn't do that right. So what is that? What number is that going to be? 0, 1, 2, 3, 4, 5. So we need to link 4 to 1. I think that work. The Earth is flat, or the Earth is round is 1, and 4 is the new one that we created right here. The speed of light is greater than 15 kilometers per hour. And sure enough, it is connected up here. And what you should notice now is that, okay, we've got our structure, but this idea that the Earth, that the speed of light is greater than 15 kilometers per hour, that has nothing to do with the shape of the Earth. But if we were to run our scoring algorithm, credence, and what happens when we run our scoring algorithm is we get this number out the other side. And let me just do this. When we run our scoring algorithm, these two are fighting one another. The scoring algorithm kind of like it's inspired by PageRank, and what it does is recursively kind of almost has like these influence one another, negating from one another until it reaches a steady state. And so if we were to say have a point that says, what do we want to say? Let's put like more weight into one of these points. Let's say a lot of people believe that the Earth is round. Then if you didn't have this here, you'd see that the Earth is round wins the credence, right? Because more people believe it. And so it's left alive. And the Earth is flat dies, right? It becomes this little gray husk of what it once was. But if we give this back in, if we put in the speed of light is greater than 15 kilometers per hour, and now we run this, you can see after it's run, both of these have died, right? Because this has negated this. And this violates our intuitions, right? We're like, wait a second, but the speed of light has nothing to do with the Earth being flat. And that's exactly why we have these linking points, so that we can protect against that. So now we say, let's create another point that says that the speed of light has nothing to do with the Earth being flat. And then we're going to, or we could even say with the shape of the Earth. And now we can link, that is going to be, if this was 4, then this should be 5. That means this is 6. I think that means that 7 now should be linked to 5. Yeah, let's try. 7 linked to 5, got entrustment, float. Like, oh, I don't know. Let me, we have a bug. 1 sec. Okay, we got it. Remember, kids, never, ever, ever make a domain specific language. Ever. Never do that. Okay, what was I saying? We have a 4-1 invalidates the Earth being flat. Okay, so we're making this new point, and we're trying to negate the idea that this is relevant to this, right? That's the whole point. We want number 6 to negate number 5. And let's go ahead and do that. So we create this new point. It's called point number 6. We're linking it to point 6 to 5. And we're saying something like the speed of light has nothing to do with the shape of the Earth. Okay. And we write that, and it gets all linked up. I guess it also gets mapped on top of this. Sometimes you get good RNG and it doesn't do that weird stuff anymore, but in our case, no such luck. And you can see that now, once again, 1 survives, right? So because we've added this new point in here, 1 survives when it in the credence, whereas before, that's going to create problems. Whereas before, 1 died, 1 being the Earth is flat, or the Earth is round. Okay, so you now have an introduction to what's called the negation game, and you have like a basic idea of how you could add these points to this graph. You could link them together. You can run this algorithm called the credence algorithm. The credence spits out this score that says essentially, like, in the end, how much, what basically, like, which one of these wins. And in this case, the one that's winning is the idea that the Earth is round. And I've also shown you that we can create an interface, in this case, a very prototype interface. In this case, something that could be prettier. But we can create an interface that you can use to add these points, and that these points can also be represented in any existing tool for any existing Twitter-like surface, like Warpcast or the Farcaster network. So now what I want to show you, and none of this is the exciting part, by the way, right? This is just a review of the literature. And by that, I mean a review of this madman's musings. And so now what I want to show you, though, is how we can use this for inference. So how can we actually search for solutions to problems by using a tool like this? And in order to do that, I'm going to need a drink of water. 1 second. Okay, I'm back. So it's always easier to understand things when you have a simple problem to work on. And here is that simple problem. So the story that we're going to be, the riddle that we're going to be trying to solve is one that you should be able to solve in about 2 seconds in your head. I just got to call 1 second. And this is the riddle of Marv, Ty, and Loy figuring out where they want to sit on the plane. So the story goes like this. Marv, Ty, and Loy are picky about where they want to sit on the plane. Marv does not want the center. Ty does not want the aisle, and Loy does not want the window. If Marv sits in the aisle, then where should the others sit? And so in order to do this, it's actually best if we just solve this problem together. So I'm going to make us the 3 seats. We have the aisle, the center, and the window. And then we just point out that Ty isn't going to go here, Marv isn't going to go here, and Loy isn't going to go here. And that should tell you that there are just 2 possible solutions to this problem. We can put Marv over here, and then we have Loy here, and then we have Ty over here. Or we're going to have to put Marv on the far side, right? So Marv goes over here. And then that means that we can't put Ty in the left, so we have to put Loy here, and Ty can go here. So these are one of the 2 possible solutions with this set of constraints. But then we know that Marv is sitting in the aisle, so of these 2, only this one can be the winner. And so we have solved this very simple riddle. But what I want to show you is that we can represent these constraints inside of this tool, inside of the negation game. And then we can move our beliefs around, and I'll show you how we move our beliefs around. And we can just, what's spit out from the system is essentially a score that says which one of those sets of beliefs is the most consistent. And so let's look at that now. So the first thing that we're going to do is we're going to set up the problem. And that means that we need to define every single possible state. Marv can be in the aisle, Marv can be in the center, Marv can be in the window, Ty can be in the aisle, in the center, in the window, Loy can be in the aisle, in the center, in the window. And you might say, but wait a second, don't we know that Ty can't be, on the left? And what I'll show is that first we want to represent all of the possible states, and then later on we can simplify it. And so when we do that, we first see a credence that comes out. This is the overall score. And this basically says they're all equally likely. And then we see all these different possible states. There's nothing to do, the circle doesn't mean anything here. It's just how the tool is laying out the points. So then the next thing that we need to do is we need to encode this idea long before we encode any of these hints. We need to encode the idea, which is kind of latent in the question, that each person can only sit in one place. And so we're going to do that here. We're going to point out that, you know, uh, Marv, if we know that if we know that 0 is true, that Marv is in the aisle, then he must not be in the center. And if we know that he's in the center, then he must not be in the window. And if we know he's in the window, he must not be in the aisle. And actually, I'm being lazy here because these are also reciprocal. So if we know that he is in the center, then he must not be in the aisle. And if we know that he is in the window, he must not be in the center, and so on. But for now, I think that we're good enough. Like the graph gets kind of messy if we add all that stuff. So I'll just add it like this. And you can see actually that by doing this, because they're all equally likely, we've said that they all have this starting value of 1. Because they're all equally likely, you know, we get this result that says, well, none of these configurations are possible because we haven't told it yet. Important piece of information. So now let me show you that important piece of information. And you can see that I have done all of this work before. And I'm spoiling the plot. And I don't want to do that. Although I'll keep this little snippet of code around because it's kind of nice. Okay, so what we're going to do now is we're going to try and bring in this information. So this is the information that we now want to represent. And let's do that. Lloyd does not want the center. Ty does not want the aisle. Or Marv does not want the center. Ty does not want the aisle. And Lloyd does not want the window. So I'm going to do that. I'm going to point out that, let's start with Marv. Marv does not want the center. And we link, what that means is that we need to make a new point, of course. I guess I need to figure out, normally I call this is like a list of deltas to a database, but here I've called it seats, since this is the seats problem. Marv does not want the center. Okay, so this is point 18. So we need to link point 18 to the idea of Marv being in the center, which is up here, which is point 1. So we're going to link 18 to 1. Hopefully it makes sense why we're doing that. And then when we get our graph out the other side, you can see that 18 is, sure enough, linked to 1. And so far, no change in the overall score, right? What we're saying is that if we received evidence that, what we're saying is that we have received evidence that Marv is unlikely to be in the center, right? And then we're encoding that into this graph. And now what I'm going to do is I'm going to do that for each of the rest of these. So I'm going to do it for Ty, and I'm going to do it for Loy, but I won't make you watch. One second. Okay, so we have implemented all these additional constraints. We have the idea that Ty does not want the aisle, and that new point that's created that says that Ty doesn't want the aisle, that's point 20. And we use it to say that that's evidence against the idea that Ty would be in the aisle. And so that is up here. Ty is up here. And that is point 3. 0, 1, 2, 3. And we do the same thing for Loy here. And so we have now represented in this system all of the different possibilities, all of the different constraints that we've been given so far, but for one, right, which is where Marv happens to be sitting. And so to do that, to represent the idea that Marv is sitting somewhere, now what we can do, I had to go and remind myself what we do. Now what we can do is we can increase. So like what you can think of is that when we build this, actually I want to show you what happens when we return what's built here, is we take this list of strings, this block of text, and we turn it into these two arrays. One of them is this small one. This is called the endorsements, and the other one is this big array, and this is called the invalidation array. And it doesn't really matter what these mean. Actually, this properly would be called the entrustments, and this is the invalidation. And broadly, what are they saying? Entrustments is saying how much has been staked in each of these. So here you see that one was staked and one was staked. Basically, the amount of money that's on the line. Invalidation is encoding all of the relationships between all of these different nodes, and so this is tracking not only the point itself and its value, but also the points that it links to, and it's necessary for building up this graph. In fact, that's what we do when we take this graph, is we put in entrustments, validation. Should have picked easier validation. Should have picked easier words. And when we do that, then we get a graph out the other side. So this is just rendering what those two things are saying. Okay, so why is this important? What does this mean? Well, what we can do is we can think about these entrustments as kind of like, what does the community think? What does everybody think? If you were to look at what everybody who has interacted with this game thinks, then this is kind of almost like, let's say it's the amount that they've staked, it's the money they've put on the line. In Ethereum proof of stake, this is roughly equivalent to literally putting your money on the line, saying, I think that this, block is good. That's not the right terminology, but you know what I'm saying. In this, what we're saying is that there's actually this additional source of information, which I'm going to introduce you to, which we're going to just create by doing np.zeros. Let's call it, I guess we already have one. That's the right length. Yeah, that's fine. We're just going to steal this. And what we've stolen here, we're going to call this the valuation. And you can think about this as the beliefs of a player. And it's the same length. It has to be the same length as the entrustments, and it's how much they believe above or below the entrustments over here. Also, I've also sometimes called this the endorsement. And let me think which is the better term in this context. I think in this context, we're going to stick with endorsement because we're going to be multiplying these together. Is that right? Doesn't really matter. Okay, and so now we're going to take this endorsement and we get what this final value that we call the endowment out the other side. Okay, I know I'm like just throwing words at you, but I find that, first of all, that what you name things matters, and it helps people keep things in their head and keep things separate. And actually, for that reason, I'm going to go back to valuation so that you don't get endowment and endorsement confused. So valuation, this is their beliefs. Entrustments, that's kind of like the amount that has been staked by the people in the community. And validation defines the relationships between of the graph. And then the endowment is just the entrustments times the valuation. So this is like how valuable is each point. Well, so right now we're getting an endowment that's exactly the same as our ingoing and outgoing entrustments. But we can do something with this that's kind of fun. And so I think I've cheated, and I can look in here and I can find, okay, some secret numbers. We're going to use these numbers to kind of imagine that we have a player in this game who believes we're going to have three different players, each who believes a different thing about where Marv and Ty and Loy are sitting. And I'll just like enumerate some of those possibilities. In fact, it'll be best if we go back up here and we look at the possibilities that we had. So up here we have Ty, Marv, and Loy. And we came up with two possibilities. Before you take into account this last piece of information, we have two possibilities about where Marv might be sitting, right? And Uh, and so that means that there's a kind of statement about where they're sitting that also doesn't make sense. So what's an example of one that doesn't make sense? Well, one that really wouldn't make sense is Ty, Marv, then Loy, since that would violate all of their preferences. And another one that might also not make sense, although it wouldn't be quite as bad, is let's just do Marv, Ty, and Loy. So this one is like the absolute worst, and then this one is the is like a pretty bad one because it violates Loy's preferences. We have evidence that Loy doesn't like to sit next to the window, and then both of these, as long as we haven't yet incorporated this information about what Marv prefers, both of these are about equally good. So let's go see if we can implement all of these in evaluation. And I'm going to show how you do one of those, and then I'm going to do the rest of them for you so that you don't have to sit through what's already becoming a long and absolutely riveting video. Tell me it's riveting. Okay. At this point, I want to before we do the next step, let's remind ourselves where we've come from and what we're trying to do. High level, we're trying to create a surface, a game that's a bit like Twitter or a bit like Farcaster that allows us to have discussions. And that at the end of those discussions, we actually get out of it a score for different kinds of different sets of possible beliefs, and the ones that seem to have internal consistency and the ones that don't, so that we can not only ourselves search for better solutions to sets of beliefs around things. For example, like, will LK99 replicate? Is the thing going around right now? Well, this would be a tool to try and figure that out. Is it consistent with the evidence that we have? If I apportion my belief in this way, then does that make sense? What new evidence would change our mind, right? That would be a new point that's added to the network, just as we added here evidence that Ty doesn't like the window or whatever. So that's our overall goal, is to create kind of like this, to do true decentralized science. And what I'm showing you here is I'm stepping you through a very simple problem, and how we can use this simple problem as an example of how the process works underneath. Obviously, hopefully what you're recognizing is that lots of what I'm doing here could be easily automated by a good user interface, and we'll get to that. But I want to show you, like, sometimes it's nice to see the nuts and bolts, kind of the unpolished version, so that you can see where we're going to go with it. And now we're zooming back in. We're talking about, okay, we've got this notion of credence, which is like some score that measures internal consistency. We have these different ideas of like the two moves that we can make in this game. We can add a point, and then we can link points together. And then we have now this notion of valuation, and the valuation is the belief that somebody brings it's their set of beliefs, the things that they think are true. And just to like kind of motivate this, if you're a fan at all of the Bayesian brain hypothesis, or of active inference, or of even Bayesian inference, you're familiar with the notion of a prior. And a prior is just a belief that you come in with that allows you to kind of like give your graph, your knowledge graph, your belief graph, a structure. And it helps to, those priors help to eliminate certain spurious ideas, and they help to bolster other useful ideas. And those priors can be moved, right? But they're just priors. And that's kind of what this is. This is analogous in the Bayesian world to priors. I think even there's a possibility that these are, you could view these as log odds, if you're familiar with that world. If you're not familiar with that world, ignore everything I just said. What we're talking about, I'm just going to give you a very simple example of how we can encode this idea of Marv, Loy, and Ty. Marv is in the aisle, Loy is in the center, Ty is in the window. The way that we're going to do that is we're going to take this valuation, we're going to name it the Marv, Loy, Ty valuation, and then we're going to go and find the things that we need to think are true, and we're going to kind of just bolster our belief on it. And so to do that, we can go up here, we can just copy this, remind ourselves of what the different states are, and oh, that's nice, thank you. Okay, that's better. And we're going to notice that, so we want Marv in the aisle. Okay, so that's 0.0. So let's make that, let's say believe is worth 3. I don't know. That's fine. We're going to say that they believe that Marv is in the aisle. Loy is in the center. So Loy sits in the center. Well, that's 7. So let's do 0, 1, 2, 3, 4, 5, 6, 7. Okay. And then Ty, where's Ty? Ty is in the window. So that's 5. So 0, 1, 2, 3, 4, 5. And so now we've encoded this valuation for the Marv, Loy, Ty ordering. And what we can do with that is we can build out an endowment by multiplying it by our entrustments. And we can plug that endowment into our credence algorithm. Credence. I think we do endowment, then invalid. And we should get a score out the other side. And here's the result that we got. You can see that in the end, what started as a 3, which we shoved in there. Here, let's just print out. What started as a 3 that we shoved in our endowment came out as a 2. So it kind of like killed off all these other ones. In fact, maybe that's an argument for just making this a 2. We're just going to double it. And so, we put in this here, and then we got this out the other side. And what this is basically saying is that these survived, right? These survived. And then these other ones died. And that makes sense, right? Because we kind of know that they should have survived. We know that Marv, Loy, Ty is one of the ones that can work with the information that we've put into the system. Now let's try and do one that we know shouldn't work. So Ty, Marv, Loy, we decided is like the worst possible input because it violates all of these preferences that we already know. And so if we were to do that here, Marv, Ty, Loy, this we expect to have a really bad score. And to do this, we can just figure out, okay, so Ty is in the aisle. So Ty in the aisle, that's 3. So 0, 1, 2, 3. And we want Marv in the center for maximum discomfort. So Marv in the center is up here at 1. So let's go over to 1 and say that this person believes. And then finally, Loy is in the window. Loy is in the window. That's 8. We were just on 7, so this should be 8. 7, 6, 5, 4, 3, 2, 1. 2, 3, 4, 5, 6, 7, 8. Okay. So I think we got that right. And now let's just make sure that we've named this right. We want Ty, Marv, Loy. And all we need to do then is we multiply that by our entrustments in order to get our endowment, and we're going to get a score out the other side. And what you should see, which is really cool, is that all of these come out as 0. And like kind of what that's saying is that this doesn't make sense with the evidence that we have access to. This is a bad solution to the problem. And so now what I'm going to do is I'm going to go in. What am I going to do? What I'm going to do before I go and encode these other ones, because there's one like final cool thing to show you, is I'm going to let's calculate a score for this. So the score that we're going to calculate, it takes back the credence, it sums it up. So it takes this whole list that's returned and it sums it up. And then it's going to divide that by, well, let's just do that first. So you can see we get 18. And when we do a sum here, you can see that we get 15. So like this number is bigger because we have more that has survived. Whereas over here, if we remember, we have less that survived. And actually, let's credence. Let's just call it C. We're going to print C, and then we're going to C dot sum. And I think that then you'll be able to see easier. See easier. So when we do these, here we get back this result. Down here we get back this result. This has all these zeros in it, where this one has some ones. And so this one has a higher score. And now you might think, okay, great. Does that give us a truth score? And the problem with this is that it depends on how much was put in the first place. But we can control for this just by dividing by how much was put in, right? So to make this clear, like what if somebody had what if this person was using a different scale, and when they believe they put 200, actually let's do it the other way around. This person puts 2 and this person puts 200. Well, now actually in this case they got away with it because because all of these got wiped out. But yeah, you can understand how if one of these had survived and it had a 200 to it, then even though this didn't make much sense, it would have had a much larger score. Like I think if we put a believe here, we would get. I'm trying to decide whether to get you to believe me on this, or here we go. So if this had a 2, I think that this should do worse. Yeah. So when this has a 2, it does worse. Because here we're putting Marv in the first seat, and Marv doesn't mind being in the aisle, right? But if like the scale that this was used on was really big, then this would get a much bigger score than this one would, and we can handle that really elegantly just by taking the endowment, the sum of the endowment, the total amount that was put in, and now we're kind of asking like a question of what's the bang for your buck that you're getting, and you can see that here. Whereas before this was just giving you, this was giving you a bigger number than this one. When we incorporate this kind of what's the bang for your buck that you're getting, we see that this is getting a much better score than this was. So hopefully that makes sense how we get this scoring algorithm, and in fact that's exactly what that little score function. So as valuations, actually this needs to be endowment. Oh yeah, this is doing something quite different, but that's what it was doing. Is you can see that it was running in order to get the credence. It was taking the sum, and then it was dividing that sum in order to get to kind of the total impact. So that's our finalized score for this system. And let's go back to where we were before. That was what we had in here. So what pops out of the other side here is that this gets a much lower score than this does, right? Not only is this something about this is just more true, more plausible than this one is, when we take into account all of the structure that we've taken into account about what we believe here. Okay, great. Maybe one fun little trick to don't doubt. Let's call one of these doubt. One fun little trick to do would be, what if we don't believe that this piece of information that we were given about Loy's preferences, what if we don't believe that that's true? So Loy does not want the window is what we said, and that was point 22. So let's go find point 22. It should be the second to last thing in the list. And let's say that we doubt it. And what we expect now, we put in this 0 here. What we expect now is that actually our score does better. That this Still doesn't do quite as well as this one does, but that it does a little bit better. And sure enough, it went from 0.55 to 0.57. And so now you should start to be able to get this idea that you could have players in this game play with setting different valuations, different possible belief sets, putting those into the system and getting immediate feedback from the system, like how well does that have internal consistency? And that then they could also ask machine learning algorithms to come up with additional nodes to add to the network, right? Points that maybe they've missed that the neural network thinks is relevant, the LLM thinks is relevant, as well as doing high dimensional search for different valuation sets that would make more sense. And that all of this would be perfectly interpretable by humans all the way down. And not only that, but ultimately consensual, right? Like this would be it's up to the human to choose what beliefs they want to represent. But the human can help to guide them and can kind of like say, well, try this out, and see whether or not this makes sense. So it's consensual, it's transparent, and it's still under human control. So this is something that I find hopeful and interesting. Maybe the final prestige here is I'm going to show you what happens when we take into account that final belief, which says that we believe that Marv is sitting in the aisle seat. And so I'm going to go set that up now, and I'll show you that in a second. One by. Okay, so I think I have represented all of these right. We have our familiar Marv Loy tie. We have our familiar tie Marv Loy. I'm going to remove this doubt. We have Marv Loy tie now. So Marv Loy tie. And we have Loy tie Marv. And what we want to do is we want to ask what kind of result do we get out of putting this in. So I think it's useful here to create a little helper function. Let's call it score. Like I did before, we're going to pass in the endowment. No, we're going to pass in the valuation, so the thing that people believe. And we're going to pass in, I guess we're going to pass in the deltas. And so we'll have to build it first, and we'll get back the entrustments and the invalidations. So valuation. Well, first we'll have to build the endowment. Valuations times valuation times. No. That goes later. We build. This is the deltas, which is in this case called seats. We then get endowment by multiplying by entrustments, multiplying valuation by entrustments, and we return the credence. The credence is going to accepts endowment, and then the second argument is invalidation. And we want to take the sum of that, right? And then we want to take the endowment, take the sum of that. And I think that is our scoring algorithm. And so now, so we want to score first Marv Loy tie, and then we want to score Loy tie Marv. Do not reload. And then we want to score tie Marv Loy. And then we want to score Marv Loy tie. And I think what we're going to get out of this is an error. Why? Oh yeah, this should be seats. Should we have said what our expectations are ahead of time? Yes. Have we failed to be scientific by not making a prediction? No, but that's a longer story. The result we're getting out does not make sense to me. I feel surprised. So what I had expected to see is that the two that we think work which we encoded up here, are Marv Loy Tai and Loy Tai Marv. So these, we think that these work. And then we think this should fail enormously, and that should fail a little bit. So here we got Marv Loy Tai Marv. Those two are working equally well. Why is Marv Loy Tai working just as well? Let's check. So we have Marv in the aisle. That's here. That's in point 0. Tai is in the middle. So that's in the center. That is 4. So 1, 2, 3, 4. Oh, I believe. That could have been the error. And then let's check Loy. So Loy is in the window. Loy sits in the window. That should be 8. So 0, 1, 2, 3, 4. Correct. 5, 6, 7, 8. 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay. Okay. That makes more sense. But now we're getting a low score for Marv Loy Tai. So let's go check that. Marv sits in the aisle. Here, 0. Then Loy should be in second place. So Loy is in the center. That's 7. 1, 2, 3, 4, 5, 6, 7. Okay. And then Marv is where? Tai is in the window. So that's 5. 1, 2, 3, 4, 5. Yeah, that's correct. So for some reason, Marv Loy Tai is not getting a good score, I believe. Okay, there's some bug. Welcome to Debugging with Connor. You thought this was a presentation. I'm sure you spotted the error. It's named or failed to rename this final one. Okay. And then this needs to go in here. Great. So now we see that after fighting with the tool, and you can imagine just how like good UX and UI can solve all of these problems, and you'll just be interacting with something that's as nice as this, and you'll be setting your valuations, maybe with little hearts or something like this. You'll be looking at graph structures. It'll be beautiful, and then you'll be getting a score out the other side, and you won't be reading indices. You'll be reading something else. But I really think that there's value in kind of interacting with the underlying machinery itself for those of you that have an interest in that kind of thing, because then you can see that it's not magic. It's really easy to understand. And my hope is that this can be demystified to the point that it is something that can be relied upon. I think that one of the things that's missing from a lot of the algorithms that we rely on is that they are mystical. We can't explain them. And so the fact that this entire algorithm is this long, and lots of actually what's in here is like, graphing stuff, is pretty remarkable that we can get all of this utility out of this incredibly short piece of code. But now let's get back to what we were looking at. So this shows exactly what we expected, right? This is the worst possible solution, and it gets the worst possible score. This is a pretty bad solution, and it gets a pretty bad score compared to these two. And these two are both equally good solutions. They both get little checks next to them. But now what happens, what I wanted to show you, the thing that I promised you, the prestige, which has taken like 10 minutes of me goofing around, is that what if we take into account that Marv is in the aisle? So in order to take into account that Marv is in the aisle, let's give some people really strong priors, right? In other words, we say, have a big belief that Marv is here. And let's give it a big number. Let's say that it's 100. So because they have this strong belief that Marv is there, that should become the dominant term. This is their prior belief. And what do we see? What we expect to see is that this first one ends up with the biggest score. And I'm actually curious to see what happens because I haven't done this experiment with all of these yet. So here we go together. That is really interesting. So because Marv being in the aisle is something that we give such high prior probability to, prior likelihood, this one, of course, wins. It has the highest score. But these other two, Tai Ma Lo and Ma Tai Lo, Marv Tai and Loy, they don't do so bad, right? In fact, this one, because it has Marv in that initial spot, it gets a pretty high score. And if we want to, remember that we can always unpack these and we can see like which ones of the beliefs are surviving that's giving it these higher scores. And this one, that number 2, which previously had some pretty strong, had a really good score. If we go back here and we just set the Marv belief to 0, right? So we have no prior belief about it. It was tied for first place for being the best score. But now once we incorporate this information that we know with really high confidence that Marv is in the aisle, well, then it can't be this one, right? It can't be this one. Because we have somebody else in a competing spot. So hopefully that makes sense of how this structure works. In fact, you know what? I think one of the reasons that this is not working for the second one is because we didn't represent the fact that if Marv is in this location, then that means he can't be in this location. And I'll bet if we added that would show up. In fact, that's really easy to add. So remember I told you that these are actually symmetric. And so the right thing to do would be to write link 1, 0, and then link 2, 1, and then link 0, 2. And I said, don't worry, it won't matter for this demo. Well, guess what? I was wrong. And I'll bet now when we rerun this, oh, that's right. Because I've added all these little points, it's now not happy because of course I've changed all the indices of, I'm using go-to statements essentially, and I'm saying, and so that's causing issues. We could cheat by okay, we're going to cheat. We're going to say 0 knows that if you're in 1, if you're in 0, that's evidence that you shouldn't be in 1. If you're in 1, that's evidence that you shouldn't be in 2. If you're okay, so we're going to do 2 and we're going to do 0. And we're going to do 1 and we're going to do 0. And I'll bet that's enough. Now that it knows that if you have evidence that Marv is in location 1, then Marv can't be in location 0. Is that the direction? Mm-hmm. Yeah, I think that's right. And so now you're going to see that score should end up being lower for all of them. Debugging with Connor 2. Oh, well, you get the point. Maybe the cycle is playing some sort of important role here. If you're in 0, that means you can't be in 2. Yeah, so I can't refactor this, unfortunately, because it'll just take too long. But hopefully you get the idea that we're what's missing from our model. Like, we actually should be unsurprised that it's not taking this into account in this result down here, that this is somehow working. And it's working because we're not representing the fact that if Marv is in location is in the center, then he can't be in the aisle. We're just missing this idea that Marv can't be in more than one place at once. And so because we lack that symmetry from our model, it doesn't show up in the final scores. And so in some sense, that's like, and we would know how to fix it. We would know how to add that node to the list if we weren't so lazy and didn't want to have to rewrite all of these valuations. So obviously you can see what the next step is. The next step is to build another layer of indirection on top of this, where you can easily, you can like name these different variables and see how they relate to one another. But I just wanted to show this to you. I wanted to show you how the underlying system works, how you can use that to figure out, which of the possibilities to believe. Now I want you to, like, as you sleep, I want you to dream about the possibility of having different valuation arrays that you are setting up, and you're saying like, okay, if this one were true, then what would happen? If this was true, then what would happen? And it's really like a extremely lightweight causal modeling tool. Like if this was true about LK99, that it's highly ferro and diamagnetic, then that would be sufficient to show the results that we're seeing in all of these experiments, would be an example. And that you could have that as one of your possible beliefs in this long list of possible beliefs. And then you could also watch as new evidence came in from the network that shifted these things around. And you could say, oh, wow, my belief on this changed, like my score on this changed a whole bunch since last time I looked. What evidence came in that must have shifted it that much? So this represents a really exciting new direction for the way that our existing platforms like Twitter and like Farcaster and like Blue Sky, like Mastodon, can be upgraded, equipped with this collective intelligence. And that can potentially save us from all the misinformation that happens on there, sure. But even more important than that, that it can accelerate the rate at which we find out new things. Okay, bye.